Good morning, grade 10s. Mr. Mitchell here, back doing our next unit. So congratulations on completing your first unit, social distancing through distance learning, and that was chapter 7 there that we did on trigonometry of right angle triangles, featuring your friend and mine, Sokotoa. For this unit, we are going to continue with trigonometry, but we are going to move beyond right angle triangles. So Sokotoa only applied to right angle triangles. And the trigonometry that we're going to do in this unit, we abandoned Sokotoa, and we're going to learn how to do trigonometry of acute triangles. So you don't have to write this down, this sheet here. I just want to go through it with you and kind of give you a little bit of the development of today's topic, and that is the sine law. So as I mentioned, with acute triangles, this is an acute triangle. Each of the three angles are less than 90 degrees. If I was to run you through this little demonstration here, so we have an acute triangle, and we do know all three sides, the length of them, and we do know all three angles. And of course, remember for trigonometry, always have your calculator set to degree mode. So what I've done below is I've done 6 different ratios. I took the ratio of side A to side B, 7.12 over 11.06, and I get 0.64 rounded. When I take sine A, the angle, and the ratio of that to sine B, I get the same number, 0.64 rounded. Likewise, if I do the ratio of side A to side C, I get 0.72 rounded. And if I take sine A to sine C, I get 0.72 rounded. And the same thing works out for sides BC and angles, the sine B over sine C. So we get the same ratios each time. So that becomes the basis for today's rule or law, and that is the sine law. So this is, once again, 8.1 sine law. And this is for, as I mentioned, for acute triangles. And the sine law works like this. If we take side A, or the ratio of side A to sine A, it's equal to the ratio of side B to sine B, which is also equal to the ratio of side C to sine C. And this can be inverted as well. So this, what I'm writing out here, is the same law, sine C over C. So you could use this however you wish to use it. And basically, we use this when we have 3 pieces of information and we're trying to find the fourth. So if we have 2 angles and a side, we can get, or we can solve for, an unknown angle. And if we have 2 sides and an opposite side, we can solve for an unknown angle. And I made a mistake. If we have 2 angles and a side, we can solve for an unknown side. All right, so if that sounds a little bit Greek to you, you're not quite understanding that, hopefully after we whip through a couple examples, it'll become much clearer to you. Now, first of all, so reminder, this is only for acute triangles, and I want to go over how we label up triangles. So drawing an acute triangle here, if this is angle A, then the side opposite to it will be side A. And the angle is labeled with a capital, the side is labeled lowercase. If this is angle B, the side across from it will be side B. And likewise, if this is angle C, The side across from it will be side C. So let's go through a couple examples. So example number 1. We have an acute triangle. It's triangle DST. And we do know a little bit of information. We know that angle D is 47 degrees. We know the opposite side, side D, is 78 centimeters. We know that the side opposite angle S, so side S, we know that it is 106 centimeters. What we don't know is we don't know angle T, and we don't know side T, which is opposite. Now our sine rule is as follows. We can say that sine D to side D is the same as sine S to side S and sine T to side T. Now, this law works. If you have 3 pieces of information, you can find the 4th. And we do want a pair of information. So we do have a pair right here. We know sine D and side D. We know this whole ratio. And we know half of this ratio. We know the side length, we just don't know the angle. So for this, we only have to use this part of the sine law. I didn't even have to write this down. I just did that to show you that we can use part of this. So we know this, we know this, we know this. Let's use it to, we know 3 pieces of information, let's use it to find the 4th. So the first thing I'm going to do here is, because I want to discover what sine D is, solve for sine D, I want to, in our law, I want to isolate that. I want to get it on its own. So I'm going to cross multiply here, and we have D times sine S. And here we have S times sine D. And to continue to get sine S on its own, I'm going to divide both sides up by D. These cancel each other out on the left side, and I have sine S. And on the right side, we still have this. You could have plugged the numbers in first and then isolated. I isolated before. Either way is perfectly acceptable. So now let's put in the information that we have. We are trying to solve for sine S, so we don't have that. We do have side S right here. It's 106. And we know this is sine 47 because it's a 47 degree angle. And that's all over 78. D, the length of side D is 78. Continuing to solve, we get 106.7314 is sine 47 over 78. Sine S, when I do 106 times 0.7314 divided by 78, I get 0.9940. And if you remember back to a strategy we used in the last unit, to solve for S, we use the inverse function of sine, and we get rounded 84 degrees. And there we go, ladies and gentlemen. We know that angle S is 84 degrees. It doesn't really get any harder than that. It's just plugging in the 3 pieces of information and solving for the 4th. So let's give a couple more examples to try, and then I'll turn it over to you. So example number 2. We have a new acute triangle. We'll call this triangle E, or I guess DE and F. And we know a little bit about this. We know that angle E is 50 degrees. We know that angle D is 54 degrees. I guess we could use our 180 rule to find out angle F if we wanted to. angle E, which is opposite, side E, which is opposite of angle E, we do not know. Side D, which is opposite angle D, we do know. It's 54 meters long. And we don't know F. And in this case, it's F that we want to find. Now, as I mentioned, we can use our 180 rule for a triangle. The three interior angles equal 180 when added together. So 180 minus 54, minus 50, that leaves us with 76 degrees. So we have 76 degrees here. So we have a pair of information right here. We know angle D and side D. And because we want to find angle F, we needed to find, because we are trying to solve for side F, sorry, we had to determine what angle F is. So we now have our 1, 2, 3 pieces of information. We could use that to solve the fourth. Actually, in this case, we're going to solve for both E and F. And of course, side E and angle E are a pair as well. And we have something here that sort of resembles a nucleus. The science geek in me is getting kind of excited. All right, let's solve for E first. So we have side E over sine E. And I'm going to have to use our complete pair here that we have. So side D over sine D. Sine E, so sine 50 is equal to 0.7660 rounded to 4 decimal spots. Side D is 54. And when we do sine 54, we get 0.8090. So just go back up here, I subbed in 54 there and 50 for the E. Cross multiplying, we get 0.0090 times E, and that's equal to 54 times 0.7660. 0. E is equal to, we multiply that out, we get 41.904. E would be 41.904 divided by, and we get 51.8. So that lets us know that side E is 51.8 meters long. Perfect. And then, so we have that. The last thing to solve is for side F. So once again, using our sine law, F over sine F is D over sine D. F over sine 76 is D over sine 54. Sine 76 is 0.9703 rounded to 4 decimal places. And we already know this from the previous question. Cross multiply, we get F 0.8090 is equal to D 0.9703. We want F on its own since that's what we're solving for. So F is equal to, I guess I can evaluate this right here. And D we know is 54. I should have written that in back here. So that's 54 times that. And we get F is equal to 52.3962. That's when we multiply that out. And when I bring this over, it becomes a divided by 0.8090. And F is 64.7. No, that's not degrees, that's meters. So we now know the length of that as well. So once again, if you know two pieces of information, you can find the third. And let's go through one more example here. Bit of a word problem, example number 3. All right, so here we have two tracking stations, 20 kilometers apart. And what they are doing is they measure the angles of elevation of a rocket. From station A, the angle of elevation is 41 degrees, and from station B, it is 75 degrees. What is the altitude of the rocket? And altitude, of course, means what is the height of the rocket. So let's try to envision this. We have station A and station B on the ground, and we know that they are 20 kilometers apart. We have a rocket up here which is being monitored by both tracking stations. We know that from A, the angle of elevation is 41 degrees, and from B, the angle of elevation is 75 degrees. We need to find out what the height of the rocket is. This, of course, here would be side A, opposite angle A. This would be side B, and side R is the 20 kilometers. The altitude, or the height, is at a right angle, so that gives us some information for our triangles. We do have two triangles here. This is not a bisector, though. There's nothing to tell us that the rocket was launched halfway between A and B. So we can't assume that this is a 10 and a 10 for this triangle. So what we have here is we have an acute triangle, and we also have two right triangles. So we can use both types of trigonometry. We can use a right angle triangle trigonometry, SOHCAHTOA, and we can also use our acute triangle trigonometry today, the sine law. So let's start to figure this out. First of all, angle R. If I use my 180 rule, so 180 minus 75 minus 41, I get 64 degrees. So I know angle R up here is a total of 64 degrees. If I also use our 180 rule for each of the small triangles, I know this is 90, 90, 75, and this would be 15, and 90, 41, and 49 is that angle. And of course, 49 plus 15 does give us 64 degrees in total. So we do have, so that's 64 degrees total. We have one pair of information here. We can use that to find, let's say, side B, since we have 75 degrees here. So let's use these three pieces of information to find side B. So B over sine B is the same as R over sine R. B over sine 75 is equal to 20 over sine 64. So I just plugged in for sine B 75, for side R 20, and for sine R 64 degrees. B is equal to 0.9659 over 20. Sine 64 is 0.8988. Cross multiply, we get B 0.8988 is equal to 20 times 0.9659. B would be equal to 19.318. That's when I do 20 times this. And I'll bring the 0.8988 over and divide it. And we get 21.5. So we now know that the rocket is 21.5 kilometers away from tracking station A. Perfect. We don't need to get side A. If you want to, because trig is fun, you can. But ultimately, when we read back over a question, we need to find out how high the rocket is, what the altitude is. And now what we're going to do is we are just going to turn to our trigonometry from last unit, and we're just going to look at this right angle triangle here. Within this right angle triangle, and perhaps I'll quickly draw it up here, we have A, we have R, and I guess this is the launch point. This is 41 degrees, this is 90 degrees, this is 49 degrees. We know this is 21.5. And because it's a right angle triangle, we can use our SOHCAHTOA. And this is what we want to find out here. We want to find out the height. So we are going to use this angle here. And if this is the angle that we use, this is the opposite, this is the hypotenuse, this is the adjacent. We have hypotenuse, and we're trying to find out the opposite. So O and H, that's our sine. So we have sine theta is opposite over hypotenuse. We know that this is 41 degrees. We don't know opposite. We do know hypotenuse is 21.5. Cool. Doing some cross multiplying, we get O is equal to 21.5 times sine 41. O is equal to 21.5 times 0.6561. O is equal to 14.1. So we know that this rocket is 14.1 kilometers into the air. Now I kind of went through two different steps here. Remember a discussion that we had before March break, and that was I probably shouldn't have presented to you this way. If this is what we're trying to find, and we do have a right angle triangle here, what piece of information would we need to be able to solve this? And the answer is we would either need to know this length or this length in order to use our trig ratio of a right angle triangle. This one here is unsolvable at this point because this rocket was not launched from the middle, so I don't know the length of this, but this one was quite solvable using our sine law. So that's what we did first to find this length. Once we had that, we had all the information we needed to solve here. So that's it, ladies and gentlemen. Give it a go. A couple things. So remember, this is for acute triangles, the sine law. Remember to have your calculator in degree mode. And if there's any issues, help out each other or contact me and I can provide some solutions for you as well. Have a great day, everyone.